turbine design for countries with not very strong winds, like Latvia. This is the wind turbine model made in Latvia from Latvian wood by Latvian hands. The main difference is the method of hurricane protection. During a storm at sea, sailors lower the sails to the deck. We can use the same technique and lower the turbine to the ground for protection against hurricane. Even though the turbine is made of very light and cheap materials, wood and thermoplastic, it will not break even during a hurricane. Please compare. Germans use a different method of hurricane protection. They put the turbine on a very heavy foundation made of reinforced concrete and make the mast out of expensive, strong steel. The production of all this iron releases more CO2 into the atmosphere than the wind turbine will save in entire lifetime. The Germans use a very strong and heavy fiberglass composite for the wings. This fiberglass composite is cancerogene and cannot be recycled, thus turning the planet into a landfill. And also heavy German turbine doesn't rotate at low wind. In Bavaria and in Latvia only 10 days a year blows strong wind enough to operate this turbine. The rest of the year these turbines stand still and doesn't rotate. But my turbine rotates even at low wind about 5 meters per second, which in Latvia happens every second day, so it pays off economically and makes a profit, and do not require taxpayer money. So-called obligatory purchase component. Here's a funny joke. This German wind turbine spins in the absence of wind. To prove to you that there is no wind, I throw a light piece of paper and it falls near my feet. I've thrown the paper up to a height, and have seen that there's no wind. Obviously, this wind turbine is powered by an electric motor. It uses electricity to produce advertisements for potential investors in wind companies' shares. The thing is, it's installed in the center of Munich near the stadium, where thousands of spectators walk by every day. Why do the Germans put wind turbines on one leg when even a child knows that a chair stays on 4 legs much more stable and requires no foundation at all? The answer is simple. It is done so that our local craftsmen Janus and Peters would not be able to put the tower on its side and repair the wind turbine themselves. For any small repair of the wind turbine, you have to order a giant crane from Berlin and pay a lot of money. Repairs are an additional income for the manufacturers of one-legged monsters. And to make the wind turbine break down faster, the Germans stabilize the main working axle with only one giant and expensive bearing. Such a bearing works in overload mode and will soon require replacement. Although all engineers know that axle is better stabilized by 2 bearings. We use 2 bearings for the main axle as well as for the pitch axles. But how to utilize unstable wind energy? It all depends on the size of your company and your wind park. For small farms, wind energy is best used for processes that are tolerant for interruptions. If there is wind power, we work. If not, we relax and wait for a new gust of wind. These are, first of all, grain milling and water pumping. In a fish breeding pond, you can aerate the water in winter under the ice. Note that the refrigerator works as a big accumulator. It can stay cold until the next gust of wind for at least a week. However, it is advisable for large-scale businesses to produce ammonia. For this purpose, wind generators can be developed so that it can directly utilize mechanical energy to compress air without converting it into electrical energy. To do this, we need to use switch cone gears, which turn the rotation at right angles. Here is a sketch of such a transmission for 1 turbine or for 2 turbines on 1 mast. The mechanical rotation is transmitted downwards to some compressor, which compresses the air to 300 atmospheres. This is necessary to liquefy the air and separate the nitrogen. Then, To produce ammonia, the mixture of nitrogen and hydrogen must also be compressed to 400 atmospheres. It is well known as Haber-Bosch process. For such approach, there will be no need for electric generator and electric motor, no need for copper, no need for neodymium magnets. It's all about saving money. In times of war, large power plants are destroyed by the enemy first. How to survive? If you distribute a lot of small wind turbines on a large area, your energy system becomes simply unkillable. After all, a small wooden wind turbine is much cheaper than the rocket needed to destroy it. The often asked question, what is the power of your wooden wind turbine? This is an incorrect question. Because you can always build more wind turbines to achieve as much power as you need. It is more correct to ask about investment cost in each megawatt hour of electricity per year. The answer is, electricity gained by our system cost you 10 times cheaper than electricity provided by single-leg three-wing monsters.
Obviously, a turbine made of cheap materials and with 3 times longer wings can easily be broken by hurricane. To protect such turbine, much more serious measures must be taken. The most radical method is to lower the turbine to the ground, just as sailors lower their sails to the deck during a storm. In practice, however, most modern wind turbines do not have this function, because they are protected from the storm differently. They simply are made of very strong, very thick and very expensive materials. Only recently manufacturers begun to come up with ways to protect against hurricanes by completely lowering the turbine to the ground. For example, this is how the French firm Alizeo does it. However, the optimal wind speed for this product is 12 meters per second. So this product is not suitable for Latvia, with its most probable wind speed is 3 meters per second. That is why it will produce only 6% of rated energy. To understand the reason why it is like this, please take a look at this graph of wind turbine performance versus the wind speed. In the middle here is a characteristic point of transition from the power's growth proportional to the cube of wind speed to maximal constant, and then to complete zero when the turbine goes to the protective position. And here is another graph. This is what the wind speed distribution looks like. To calculate the real annual average power, you need to multiply these two functions and take the integral for all speeds. I have written a paper with all the mathematical formulae and exacting proof. I hope it will be published. The result is as follows. As soon as in Riga the average annual wind speed is 4 meters per second. The Alizeo turbine with its optimal wind speed about 12 meters per second will produce only 6% of its rated energy. Meanwhile, a more sensitive turbine designed for winds about 5 meters per second will produce 45% of its rated power. That's 8 times more than Alizeo. So my aim now is to create the turbine that works efficiently at wind speeds of 5 meters per second and stops completely at wind speeds of 10 meters per second. Not ready yet, but I am working.
We are looking for buyers for small wind turbines that we are already producing.